Hello everyone, in this video I am going to prove this theorem, which is known squeeze principle or sandwich theorem, by using direct proof technique. And end of the video I will give you one example which can be solved by using this theorem. Let's start. If you want to prove one theorem by using direct proof method, you should separate your theorem into two parts, the assumption part and the result part. All theorems have these two parts. Consider this theorem. This theorem says that if an is less or equal than bn and it's less or equal than cn for all values of n, this is an assumption, and also limit an equals limit cn and it equals l, this is another assumption, right? Then the result is coming, limit bn is l. This is what we are going to prove that by using our assumptions. We have two assumptions and we have only one result. We need to prove that result by using that assumptions, but how? First of all, limit an is L. This is a convergence sequence, so we can use the definition of convergence sequences, right? What was the definition of convergence sequences? For all values of epsilon, there exists n1 such that for all n which is greater than n1, absolute value of an, it converges to L, so it is minus L, must be less than epsilon. This is the definition of limit an equals L, right? And also, limit Cn is L as well. So we can easily say that there exists n2 such that for all n which is greater than n2, now we have absolute value of Cn minus L must be less than epsilon. But we are trying to prove that limit bn is L. We need to find some kind of like definition like this, but absolute value of bn minus L must be less than epsilon. But how can we find that? I'm going to say that let n is the maximum value of n1 and n2. Why? Because then when I say that for all values of n which is greater than n, it satisfies that for all values of n which is greater than n1 and n2 as well, because n is the maximum value of n1 and n2. So when I say that for all values of n which is greater than n, I still have this inequality and this inequality at the same time. So I'm going to use these inequalities. What was that? The first one is absolute value of an minus L is less than epsilon. And the second one is absolute value of Cn minus L is less than epsilon. You remember the definition of absolute value, right? If something if an minus L is less than absolute value of an minus L less than epsilon, it's still less than epsilon but greater than negative epsilon, right? This is the definition of absolute value. Similarly, Cn minus L will be less than epsilon but greater than negative epsilon. This is the definition of absolute value. Now, we came here by using this assumption. Now we are going to use that assumption. That assumption is an order between an and Cn. An values are less than Cn values. But in here, as you can see that we don't have only an, we have an minus L. So if I add plus L for all sides, and similarly we have Cn minus L. So if I add plus L for all sides, what do I have? I have that L minus epsilon. I have only an because an minus L plus L will be an, and L plus epsilon, right? And also similarly, as you can see, we have that part. Now the lower bounds are same. The value an and Cn, both of them are greater than L minus epsilon but less than L plus epsilon. So I can write that. Consider the lower bounds are same and the upper bounds are same. So we can write them like this. L minus epsilon between L plus epsilon. And we know that an is less than Cn, right? I can write here an is less or equal than Cn. But also I can write an is less or equal than Bn is less or equal than Cn, right? Because that was the assumption for all values. I have that inequalities. Now I want to say that do not consider an and Cn. Just only consider Bn. Bn is between L minus epsilon and L plus epsilon, right? Now if you add minus L for all sides, you can see that that one will be minus epsilon, Bn minus L, and this is epsilon. So this is the definition of absolute value. Absolute value of Bn minus L is less or equal than epsilon. Now we prove that for any epsilon which is greater than 0, there exists n such that for all n which is greater than n, we prove that absolute value of Bn minus L is less than epsilon. So this is the proof of limit Bn is L. So we prove that theorem. That's it. Now I want you to give an example for you. Let me write it in here. Example. What is the answer of limit when n tends to infinity sine n factorial over n? It looks like so hard, right? But if you know that theorem, it will be very easy. The only thing you should know about this example is the sine function. You know the sine function is a bounded function. Consider sine x. Whatever x is, sine function is always between -1 and 1. So if you say that it is sine n factorial, it doesn't matter. Sine function is bounded, so it takes values always between -1 and 1. But in this example, we are looking for sine n factorial over n. So we can divide all sides by n. And also in this example, they ask that what is limit when n tends to infinity sine n factorial over n? So we should take limits when n tends to infinity for all sides. We have sine n factorial over n and limit n tends to infinity 1 over n. Now can you see that or not? Limit when n tends to infinity -1 over n, it tends to 0, right? Similarly, limit n tends to infinity 1 over n tends to 0. So you can think that this is an, this is Cn. So as you can see that this is the sequence Bn. Bn is always between an and Cn. So an converts to L, which is 0 now, and Cn converts to L, which is 0 now. Now we can easily say that limit Bn, which is sine n factorial over n, is 0. So this is the result of that example. Thank you for watching my video. If you want to see more real analysis videos, you can subscribe my channel. Thank you.